In this module, we're going to talk about nuclear power. Now, you may remember from previous modules that we looked at the energy density of different fossil fuels, coal, natural gas, oil, and I mentioned that even food that's stored chemical potential energy, they all have about the same amount of stored energy per kilogram, a few tens of millions of joules in a kilogram of stored chemical potential energy, a kilogram of fossil fuel or oil or something like that. Nuclear power does not come from chemical potential energy. It comes from not the electronic force that holds atoms and molecules together, but it comes from the strong nuclear force that holds the protons and neutrons of the nucleus of an atom together. And so just as the electrons in molecules can sort of act like springs to keep those things scrunched up, and that stores some potential energy which can be released if those things break apart by reacting with other atoms through combustion. Some atomic nuclei are storing energy like bunched up springs. Remember, they're mostly protons with neutrons, and protons are positively charged. They want to push away against each other. And the strong nuclear force overcomes that electrostatic repulsion and holds them together. But if that breaks, then you release a huge amount of energy. And in fact, the nuclear potential energy is about 10,000 times greater than the chemical potential energy in fossil fuels and food. So you get a tremendous amount more energy per kilogram of fuel. So that's what we're going to be talking about in this module. And around the world, nuclear power has been used, and in some countries, for example, France most notably, uses nuclear power for the vast majority of their electricity. They made a decision as a society some decades ago that they were not going to be dependent upon importing fossil fuels. They don't really have much in the way of fossil fuel resources themselves. And so to generate electricity, they decided they were going to go nuclear, and the vast majority of their electrical energy comes from nuclear power. You can see that for the United States, it's listed here as about 20% of electricity coming from nuclear power, and this figure is a few years old. It's somewhat less now. Uh, the number of nuclear reactors shown here. France gets most of its electricity from nuclear power plants with about 60 nuclear reactors. The United States, of course, uses much more electricity than France does as a bigger country and a more energy intensive country. We've got about 100 nuclear power plants in the United States. There are two currently operational in Florida. You can drive by one down on the Atlantic coast if you head down south from UCF on US 1. You'll see it. As with most thermoelectric power plants, you need a source of water because just like a fossil fuel burning power plant, nuclear power plants generate heat to boil water to produce superheated steam and use that steam to spin a turbine connected to an electrical generator. Then you get some warm wastewater out on the other side, which you have to let it cool off before you dump it back into the environment. So most of these power plants are near natural bodies of water. Let's remind ourselves about the structure of an atom. The nucleus, as I mentioned, is composed of protons and neutrons, positively charged protons and neutral neutrons. The behavior of an atom, how it acts and interacts with the rest of the world, is really governed by the electrons, which are in this cloud at a great distance away from the nucleus. And this is a cartoon drawing in this slide here that is not at all to scale and not really a good representation. It's just a reminder that the nucleus has the positive protons and the neutral neutrons, and then surrounding that are the electrons, and in a non-ionized, in a normal atom, the number of electrons equals the number of protons. However, the number of neutrons does not necessarily have to equal any of those things. And in fact, even within a particular element, a particular type of atom, that's determined by the number of protons in the nucleus, I can have different numbers of neutrons. So we talked about this in Module 1. So now let's come back and take a look at this again. Here in this slide, you see three different elements: hydrogen, helium in the middle, oxygen on the right. What defines an element is the number of protons in the nucleus, which again determines the number of electrons surrounding that nucleus. And it's those electrons that determine how it makes chemical reactions, how it interacts with light, whether it's a liquid or a gas or a solid at room temperature, what it tastes like. All the characteristics that we're familiar with matter are determined by those electrons. And so that number is determined by the number of protons in the nucleus. So that's what defines an element. That's what says this is an element of hydrogen, not an element of helium, and so on. However, for any particular element, you can have a different number of neutrons in the nucleus, and those are called different isotopes. So in the example you see here, there are three different isotopes of hydrogen shown, two different isotopes of helium, and two different isotopes of oxygen. So on the far right, oxygen has an atomic number of 8. That means 8 protons in the nucleus. And oxygen 16 has also 8 neutrons. So 8 protons plus 8 neutrons makes 16. So that's oxygen 16, but there's another isotope of oxygen that has 10 neutrons in the nucleus. It still has 8 protons, so it's still oxygen, but it's got 2 extra neutrons. That makes it a little bit more massive. So that's the definition of isotopes. That's a reminder of what isotopes are that we first encountered back in our introduction in in module 1. So in this part of this module, we're just going to introduce the concept of radioactivity. So you may be aware, have heard that subatomic particles are governed by quantum mechanics, which are described by probability distributions. And so the behavior of subatomic particles is not individually deterministic, but can be described by probabilities of what those particles will do. And that's the case for radioactive decay of an atomic nucleus. Remember that those positive charged protons, there's an electrostatic force that's trying to push them apart. There's this other fundamental force of nature called the strong nuclear force that when those particles get very, very, very close together, that strong nuclear force overcomes that electrostatic repulsion and it binds them together. Neutrons, in some sense, help keep those things stuck together. They put a little bit of space between the protons. They contribute to that nuclear strong force that binds the nucleus together without contributing additional positive charge. But as we get to larger and larger nuclei, some of them can be unstable. And the description of their instability is by a quantity called the half-life. So if I have 1,000 atomic nuclei that are identical of an element and an isotope that is radioactive, and it has a half-life of, I'm making this up, 1 year. What that means is that after 1 year, on average, half of those 1,000 atomic nuclei will have decayed. And we'll talk about what happens in the decay a little bit later. But that would mean that after 1 year, I would have 500 left of the original radioactive atomic nuclei unchanged, but the other 500 would have decayed into some other products. They would have broken apart and become something else. I've still got 500 of the original thing. If I wait another year, half of those will have decayed. That's another 250 will have decayed. That means after 2 years, I would have 250 left of the original nuclei, 750 would have decayed. Now, if I wait 1 more year, half of those 250 that are remaining will decay. I would have 125 of the original stuff left, 875 would have decayed. Then if I wait 1 more year, half of 125 is 62. I would be down to 62 or so atoms of my original 1,000 radioactive atoms and 938 decayed atoms, and so on. And so the half-life, I went through that deliberately here, and it's using the same numbers that you see on this graph. And what you see in this graph, the red curve is showing the number of undecayed nuclei as a function of time from your original sample. And you see that after each half-life, half of what is remaining decays. That is not the same as half decays in the first half-life, and then the other half decays in the second half-life, and so after 2 half-lives, you'd be at 0. It's half of what's remaining. So these guys don't get together and talk to each other and know what they're all doing or coordinate anything. Each half-life period of time, the probability is that half of those radioactive atoms will decay. There's a very nice demo that we could do if we all got together, and if you are in a group of people that's large enough, you can give everybody a coin and have everybody stand up and flip the coin. And if they get tails, they sit down, and if they get heads, they remain standing. And if you do this with a large enough number of people, you'll see the number of people standing will follow a curve just like this red curve. After one flip of the coin, roughly half those people are going to get tails and sit down. Well, then everybody who's standing flips the coin again. Well, that penny doesn't care if it was heads or tails before. It's still just got a 50-50 chance of coming up tails. So if the ones that are still standing, about half of them are going to get tails and sit down, and so on. So that describes the rate of radioactive decay. Radioactive decay of these atomic nuclei is called fission, splitting apart. And atoms that are more massive than iron, when they split apart, liberate energy. And we're using, in our nuclear power plants, generally uranium, has 92 protons and over 100 neutrons in the nucleus, and they split into smaller atoms. And when they do so, they release energy that is stored in that nuclear potential energy. And the amount of energy is given by E equals mc squared, the most famous equation in the world. C is the speed of light, which is a very big number. So c squared is a very large number. M is the amount of mass that gets converted into energy, E. And the stored energy, the stored nuclear potential energy in these atomic nuclei is actually in some of the matter. So when those things break apart, there's less mass than what there was originally, and that mass has been converted to the kinetic energy of those products. So this is a description of, or a summary of what the half-lives are for some radioactive elements. You can see uranium 235, that's one particular isotope of uranium, has a half-life of 700 million years. Uranium 238, a different isotope, and the most common form of uranium that we find naturally, has a half-life of 4.5 billion years. And the uranium isotope that we use in our nuclear power plants is the uranium 235, which you can see is less than 1% of natural uranium. And so for our nuclear power plants, the ore that is dug up is uranium 238, and then we separate it out and remove the uranium 235 and enrich it in uranium 235 to be fuel for our nuclear power plants. So the last slide is just a reminder that radioactive doesn't mean that there is light associated with this. It has to do with the particle decay, a massive atomic nucleus splitting into several constituent subatomic particles which carry kinetic energy away. And there are 3 different main types of radioactive decay. They are alpha decay, which emits, among other things, potentially a helium atom; beta decay, which emits an electron and potentially other things; and gamma decay, which is when a gamma ray, a high energy photon of light, is emitted. And the total mass of everything after that decay, if you add it up and put it on a scale, is less than the mass of what you had in the first place. And that missing mass is the M in E equals mc squared. So look at the example problems on solving problems with radioactive decay, and we'll see how that feeds into the production of energy in nuclear power plants in the next part.